Good morning, everyone, and welcome to MAE 209, Probability and Statistics. My name is Richard Kohar. Hopefully you can hear me okay. Yes. Make sure I see something in the chat that you can all hear me. Okay, yes. Which picture are you referring to? Somebody was just saying that they a picture in the chat. Perfect. Okay. So from our previous lecture, we did in lecture 17. Oh, that's on the waiting screen. It's a generic photo, stock photo. It's not of Kingston. Okay, so previously we were talking about the normal distribution in lecture 17, and we had left off with the example of intelligence that intelligence is usually measured with an intelligence quotient, and when we test it on a population, it usually follows a normal distribution. And every couple of years we have to normalize it for the next generation, and we normalize it such that the mean is 100 and that the standard deviation is 15. So we had calculated what the probability that somebody randomly selected has an IQ above 130, and that it's a 2.3% chance that that's, or 2.3% of the population have an IQ greater than 130. And we also had that exercise where I asked, find the probability that a person has an IQ within one standard deviation from the mean or the expected value. So to do that, we can write out the probability, and you have the mean minus the standard deviation is less than or equal to x, which is less than or equal to the expected value plus the standard deviation. And so what that would give us is what we want. What we would like is that area here. So if we do that calculation, again, we're taking the CDF up to 115 minus the CDF up to 85, and we have to normalize it. So we have to write this. So from here to here, what we're doing is converting it to the standard normal. So again, remembering that we're using x to represent the normal distribution of the test, the IQ test, and we're transforming it into this new variable z, where the mean is 1 and the variance is 1. Sorry, the mean is 0 and the variance is 1. So again, we can transform it back to z less than 1 minus z less than minus 1. And so doing those, finding it on our standard normal table, we get this number, which is 0.6826. And this is what we would expect. The reason for that is what we're going to talk about is the empirical rule. I had posted exercises for the remaining of the chapter 4. So check that out on Moodle. So now we can start to discuss what I was talking about, that empirical rule. So we're within one standard deviation, and we would expect that approximately 68% of the data or the population to lie within that. So we can start off with our lectures 18. Oops, it shouldn't be the function, it should be the distribution. Okay. So I have some of these notes already scanned and posted online through Moodle, so you don't have to write out the things that have already been pre-written. So there's a PDF available through Moodle. Okay, so the empirical rule that we're looking at today, what I was saying before, that the data within here between one standard deviation is 68%. And so if the population of a variable is approximately normally distributed, then 68% of the population is within one standard deviation of the expected mean. And it should be expected value / the mean. And again, like I said, here's the mean, and it's within one standard deviation, and it's 68%. So that's what just that illustrates. Same thing. If there's two standard deviations, then it's 95%. And if we go out 3 standard deviations, that we get close to almost 100%. So 99.7% of the population is within 3 standard deviations of the expected value. Moving on. Approximating the binomial distribution using the binomial distribution. So the idea is that if you have a binomial distribution like this, as long as the binomial distribution is fairly symmetric, meaning that I kind of have, if I draw this line of symmetry right through here, that this is symmetric. So if I look on the left-hand side, it should match what is on the right-hand side. And same thing here and here and here. So again, if it's fairly symmetric, you can approximate this discrete distribution using a normal distribution. So here's the proposition. If you have a random variable, call it x, and it's binomially distributed with the parameters n and p, again, if the binomial histogram, or your graph of the PMF, is not too skewed, then you can approximate this random variable using a normal distribution. And for those two parameters that we have for the normal distribution, mu and sigma squared, well, instead of writing, well, we have to base it off the parameters that we have with the binomial distribution. So for mu, we use NP. Again, that's the expected value of the binomial distribution. And over here, we use the variance of the binomial distribution. So in other words, well, we can calculate the probability, the CDF, or the cumulative distribution function, that the area under the curve to the left of x plus 0.5. So we give a little bit of a what's called a continuation correction. So just a little bit past x. So this is what we can have. That if you want to do the CDF of it, of a binomial distribution, that it becomes x is less than, so the particular value of x that we're integrating up to, plus 0.5, so that's our correction, minus mu, and in this case mu is NP, all over the standard deviation. And so in this case, oh, and I wrote q. I should be careful because most of the time, a lot of people will write q, and I prefer to keep writing out 1 minus p. It's one less letter to remember. And so in practice, the approximation of the binomial distribution to the normal is good, provided that the number of trials times the probability is greater than 10, and the number of trials times the probability of failure is greater than 10. So that should ensure that you have a fairly symmetric binomial distribution. And since the underlying binomial distribution is symmetric, then you can apply it. So just as a small remark, the result is not as important as it used to be. And the reason for that is because we have calculators now. It's very easy now to calculate the CDF of the binomial distribution using, say, Excel or MATLAB or any programming language of your choice. So another way you can think of it, of kind of demonstrating a binomial distribution, is let's say that I have a pegboard. And so at this point here, I could drop a ball and it will either go left or right. Same thing here, same thing here, same thing here. Okay. So as we drop down, we'll assume that it goes with probability 1/2, that it either goes to the left or to the right. So it can fall down and go this way or this way. When it hits this one, it can either go left or right. It can go left or right here. And so what's interesting then about this is that, okay, how many ways are there to do this? Well, there's only one to get to this point right here. There's two there's only still 1 to get here, as well as to get to this point, as well as to get to this point. Over here, again, 1 way to get there, 1 way to get there, and 1 way to get here. But if we sum up the 2 paths here to get to this point, that gives us 2. And over here, there's 3 paths to get to this point. There's 2 plus 1 gives us 3 paths as well. And over here. Oh, somebody has already noticed it. So yes, this is starting to look like Pascal's triangle. So if you want to think about that, you normalize it, you have, well, this is on the, so that would give us 8. So over here you would have 1/8, you would have 3/8, 3/8, and 1/8. So if you wanted to predict what the probability of a ball landing at these pegs, you know, it looks something like that. Okay. Now what happens is, that's not a great curve, but yes, you can see that this is symmetric about this axis right here. And I suppose you could actually start to fit a curve right through here. So again, there's kind of a normal distribution, and that's what we'll be eventually seeing. Things like, as we, in the limit, as we have like infinitely many pegs, that instead, you know, we'll have 6, 4, 1. So you can keep making this longer and longer and longer, and what ends up happening is you get more of a refined binomial distribution. So again, what you're seeing is that p is equal to 0.5, and then n at this case, my pen is, so we have 1 plus 4 plus 6 plus 4 plus 1 gives us 16. So again, that's not big enough yet. What we usually want is somewhere, say, around 50. And when we get to 50, that would be large enough that, again, it starts to form a nice normal distribution. Okay. Move that out of the way. So, at a large university, for instance, let's say that 25% of the students receive financial aid. And we're going to say that the number of students in a random sample of size 50 is represented by a random variable x, which is binomially distributed with n equals 50, and p, the probability of success of finding that student that we want, is 0.25. So we can use the normal distribution to approximate the probability that at most 10 students receive financial aid. So yes, we could plug it into a binomial distribution and calculate what that should be. But instead, what we're going to do is we're going to use that approximation. We're going to use this. Okay, so so that's kind of our capital X, is less than, so our value in this case is 10. We have that continuation correction, that going from discrete to continuous, so it's plus 0.5, minus our expected value mean, so it's NP, so it's 50 times a quarter, well, maybe I'll write out the NP, so 50, there we go. All over, and we need the standard deviation, and that's 50 times 0.25 times the probability of failure. So in this case, plugging that in, we'll get minus 2 on the numerator, and in the denominator, so I get minus 1.51. Now, is everyone checking to make sure that I did that correctly? Make sure that that number is correct. Yep. Okay, good. So what I can do then is I go over to my normal distribution table, my standard normal table, and I look for minus 1.51. So again, and I thought I had my second ruler, but what I do is I just go down this column right here, so 0.0655. Okay. So therefore the probability six point 6.5% chance that at most 10 students receive 8. So same thing we can do for this one. We'll do the CDF up to 10 minus the CDF up to 5. Now we've already calculated what 10 should be, so let's not waste the calculation, so we'll have that there. And we have to then calculate for it for 5. So calculating that using calculator, we have 5 plus 0.5 minus 50 divided by square root . So I get minus 2.29 . So again, I'll pull out my table, minus 2.29. Last one right here, 0.0110. And subtracting that, you get 0.0545. So that there would be a approximately, say, 5.5% chance that between 5 and 10 students, and notice that this is inclusive, receive financial aid. Okay. Okay, so we move on now to section 4.4, which is the exponential and gamma distributions. And I think for today, what I'm going to do is I'm going to just work through the exponential function. And we will cover the gamma distribution as well. So for now, this is what we'll use. So we have the exponential function. Just a second. Okay, and it's a fairly important because we use it in engineering and science disciplines, but in particularly, we use the exponential distribution when we start to talk about distribution of times between events. And when we start to talk about distribution of times between events, then we get into a subject called queuing theory in mathematics. And we also get into structures which we call Markov chains. So Markov chains are fairly useful and commonly used in engineering for modeling. So the exponential distribution is fairly useful. So the parameter that we are going to work with is the gamma, and it's going to be a positive value. And this is the probability density function. So we have our function, and it's for values of x that are non-negative. And so if it's non-negative, then it's just gamma times the exponential function to the minus gamma x. And so you might be thinking, what does that kind of look like? Well, say for 1, this would be, say, around 0.5. That's what that exponential function looks like when I have, say, lambda is equal to 1. And so when you have this negative in the exponential function, it's not exponential growth, but it's going to be exponential decay. So it's decaying over time, and it gets smaller and smaller. The other thing to note, here's a question then. What's the limit as x goes to infinity of lambda e to the minus lambda x? So what in the chat, can you just tell me what that value is? Yep, it is 0. So as I'm going out to positive infinity, that these should be getting close to 0. So you can say then that if you were to graph this, that this y equal 0 is then a horizontal asymptote. Horizontal asymptote. And it starts at x greater than or equal to 0, so it means that nothing is defined on the left-hand side of x equals 0. Yes. The next thing that we have is the CDF. So we can integrate under these curves here, and when we do up to a certain point x, then we get the cumulative density function. So in this case, it's 0 if it's less than x, and then if it's greater than or equal to 0, we use 1 minus e to the minus gamma x. So again, in this case, what that would be is that area is 1 minus e to the minus gamma x. Okay, so there's a question that was asked. So the question that was asked was, why doesn't lambda equal 1 go through okay, well, yeah. Well, let's substitute this in. So using our PDF, we'll use 0, and lambda is going to be 1. So I'll have 1 times e to the minus 1 times 0. That is a very good observation. Thank you for catching that. And the answer is it should go through 1. Okay. So the other two things that we have for characteristics of the exponential distribution, so we have the PDF, the CDF, and the other two things that we have is the expected value and the variance. So the expected value is 1 over lambda, and the variance is 1 over lambda squared. So what we should do is show you how we got that CDF. Okay, so in this case, what we're going to do is we're going to show that the CDF is correct. So okay, so what we're going to do is we're going to show that. So again, if x is less than 0, just by the PDF, then the function is 0. Okay. And if we look at the PDF again, if it's greater than 0, so using our definition, it's usually from minus infinity up to x of the PDF function, and I'm using a dummy variable y, and there's our parameter lambda dy. Now in this case I don't have to worry about going all the way to minus infinity because that's not part of the domain of the function. So what I can do then is rewriting this. I just have to worry from 0 to x. And I will write in the function using my dummy variable. The lambda doesn't depend on y, so I can bring that out in front. It's a constant in this case. And now we need our technique of integration. So these are one of the basic integration techniques, which is integration by substitution. So I'm going to, just over here, I'll write e to the minus lambda y dy. And this is substitution. And so for this substitution, I'm going to just replace what I have in the exponent, minus lambda y. And I also need my du. So when I differentiate this, I get minus lambda dy. And I need to just kind of rearrange that. So bringing that minus lambda to the left-hand side. So now I can do my substitution. I have e to the u, and my dy is du over minus lambda. I can bring that minus lambda out front. So the integral of e to the u is e to the u plus a constant. And then I substitute my u back in. So in this case, it's minus lambda y. So that's what I need. So over here, it's going to be lambda. And inside the bracket here, it's going to be minus 1 over lambda e to the minus lambda y from 0 to x. So substituting in my values now. And for 0, I get 1 over. I also have to remember, make sure I don't drop a negative. So I have a minus, and then I have a minus there, so that becomes positive. 1 over lambda. And if I substitute in y for 0, that gives me 0. So that's just e to the 0, which gives me 1. Okay, so now I can distribute this lambda. So I get minus lambda over lambda, e to the minus lambda, plus a lambda over lambda. So that's 1. And so I'm left with 1 minus e to the minus lambda x. So, therefore, I have my two cases that I considered, my x less than 0 and x greater than or equal to 0. as required. So what I have done is a proof. So again, all we had to do was just integrate to show, integrate the PDF to show the formula for the CDF. Okay, so is there any questions? Does everyone remember some of their techniques then from first year calculus? So what's the next one that we're going to do? We're going to look at the expected value. We'll do the expected value and the variance. So what we need to show then is that the expected value is 1 over lambda. So show that the exponential distribution is that the expected value is 1 over lambda. So here's our proof. What we're going to do is we need our definition of what the expected value is. And so our expected value is the value times the PDF. Or you can think of it as the value times the probability of that value. And then we integrate it over the entire real line. So that goes from minus infinity to infinity. And again, we just need to look at the domain. So we see that it's non-zero when x is greater than or equal to 0. So I just have to integrate from 0 to infinity. So here's x, and I copy down my PDF. Lambda e to the minus lambda x dx. Okay, so with this, what things can we do? Well, I can pull out that lambda because it's a constant. So now I'm left with the integral of x e to the minus lambda x dx. What technique should I use for integration? Does anyone have a feeling about or an intuition of what technique by parts? Yes. So this is the part where I get to briefly say what integration by parts is. Oh, not by substitution. We're going to be doing it by parts. And the reason for that is because I have two parts right here. I'll have here and I have here. So integration by parts. I might abbreviate it as IBP when I write things. And we have UV oops. What I need is the integral of u dv. It's going to be integrating from a to b is equal to uv evaluated at a and b minus the integral of a to b v du. So I'm using the integration by parts. I'm going to have my two functions. So again, I have my u and my dv. So this is going to be my u, and over here will be my dv. Okay, and if I differentiate, I just get dx. And now I'm going from dv to v, so I need to integrate. And oops, I should. Let me just extend that a little further. So it includes my dx. So I can then integrate that. Is 1 over lambda e to the minus lambda x. Now, if you want to check to make sure that I did this correctly, all you have to do is differentiate that. So differentiating, just looking at this part right here, differentiating that, it's itself, and then times the derivative of the exponent, so just by chain rule, and or sorry, you need to take the derivative of this, and so it's 1 over the derivative of this, and so you would get back to dv. Okay. So what I'm going to do is I'm going to start applying the rule then. Integration by parts. So I have my u and v. So I have a minus, so I have x. I have my lambda on the bottom there. I have a negative, and I also have e to the minus lambda x. It's going from 0 to infinity. I have to subtract it, and then I'm going to be integrating from 0 to infinity of v du. So what I can do is I can substitute in my value. I have infinity. So for the first value, if I have infinity, so I have e to the minus infinity. So I have lambda and then positive infinity. That gives me 0, right? Because that we had already established. So that would be 0. Subtract. And then I have another one which is 0, and if I substitute in that value 0 into this over here, that gives the whole thing 0. So it's 0 for both of them. I have a minus and a minus, so that becomes positive. I'm going to bring out that 1 over lambda, bring it out front. Okay, and again, what I can do is integration by part, or sorry, my substitution rule. And I'm almost finished with this. I just have to substitute in my minus lambda. It's constant. So that's it. So I don't have to worry about that 0 there. I have 1 over lambda. And then I need to have this integral. E to the minus lambda x from 0 to infinity. So when I substitute in this value here, what I get is, over here is 0. And then I have a minus, and a minus gives me plus. And I put in 0 in here, and I get e to the 0, which is 1. So I'm just left with 1 over lambda. And if I distribute this, I get lambda over lambda, so that's 1. Or I just kind of multiply that together. Get 1 over lambda. And so that simplifies down to just 1, so I get 1 over lambda. So what we have shown then is that the expected value of the exponential distribution is 1 over as required. So what we should do is take a 10-minute break. But before I do that, because some people might want to keep working on something like this, we're going to prove also the variance. So we're going to show that the variance is 1 over lambda squared. And so that proof begins by using the variance formula. So we have the expectation of x squared minus the expected value squared. And so what we have this value already. We already calculated that. That's 1 over lambda. And what we need to do then is we need to do the expected value of x squared. And by definition, it's its value. So in this case, it's x squared times the function, or the PDF, and I shouldn't use, my domain is going to be still from 0 to infinity. And I still will have a lambda e to the minus lambda x dx, which again I could factor out that lambda. And so that's the integral that we'll have to tackle. So you will have to use integration by parts again. So try that during our 10-minute break, and we'll resume in 10 minutes. And if you don't want to work on that right now, it's okay. We will take this up when we return. Okay, so let's resume. So how many had actually tried doing that integration? Just in the chat. And how many went and got coffee? I got a coffee. Okay. Well, I've also posted a team coffee. I don't even know what a team coffee is. Power nap. Okay. What I've also posted is a small poll just to quickly get a sense of how many people would want some extra some notes for integration that I can just post through Moodle. So, kind of looks. Yeah, there's some people that want some notes. So I can post some as a little bit of a review. But again, this is stuff that we've covered in 101. But sometimes we forget. And speaking of that, do I remember what I was saying before? Yes. We have to use integration by parts. So again, here is what I will call my u, and over here, this is what I'm going to call my dv. So I have my u dv. So in this direction, I'm differentiating, so I want 2x dx. And over here, I want to differentiate. Or sorry, I want to integrate. Okay, so that's what we're going to use for our integration by parts. So in this part, I need to have my u dv is equal to uv, so it's x squared times v, so that's e to the minus lambda x all over lambda. And that needs to be evaluated from 0 to infinity minus, I need my integral from 0 to infinity of v du. So substituting in these values here, I got infinity. So again, for this part here, e to the minus infinity gives me 0. So that's 0 for that part. Minus, and then I have a minus, so that becomes positive. And I'll have 0 substituted in the x squared, so that becomes 0. So that's still 0 there. I have a minus and a minus, so that becomes positive. I have a 2 I can factor out, or I'll bring out to the front here. I can also bring out the lambda, and I'm still left with 0 to infinity of x e to the minus lambda x dx. But this is something I am not. We are lazy mathematicians. So what does that mean? I'm not redoing all of that again. We already know what that is. So this one right here, this, because we had already done it here, it's just 1 over lambda. Okay, so what we get then is lambda is 2 over lambda times over lambda Did I make a mistake? So just double check this. So again, we should have our expected value is 2 over lambda squared. And which is what we were required. Yeah, so just remember that I have here, when I have my integration, I have a lambda, and that goes down to 1 over lambda. So what I was looking for is really I should have I should have been a little bit more particular about this. Again, I had lambda times 1 over lambda times 1 over lambda. So that gives me lambda times lambda squared, which gives me the 1 over lambda. But for this integral that we had done, which is what I was looking at here, the integral from 0 to infinity of x times e to the minus lambda x dx should be 1 over lambda squared. Okay. Again, because we had factored out, so essentially that's what we needed. And you just kind of cover up that part. And that's what we needed. Okay. Thank you for letting me have that pause. It just needed a moment to convince myself. So is everyone okay with that so far? So essentially what we had done is integration by parts twice. We had to, because we have x squared, we applied it once, and we have this 2x here. And again, we can pull out that 2 and the lambda out front, but we now have x e to the minus lambda x. So again, integration by parts. Or what we had done is we'd used our work that we'd done from our proof. Okay. So we also then got to cover some of the review for integration by parts, integration by substitution. Those are our two big tools that we'll need in this course. Somebody was asking me if we need to know some trigonometric. As far as I know, not yet. I don't think so. But that's excluding if we start to do like probability on circles or something like that. Then maybe. So here's an example of using the exponential distribution. Suppose that for certain types of bridges that an exponential distribution describes the stress range in a particular bridge connection with an expected value of 6 megapascals. What is the probability that the stress range is at most 10 megapascals, and what's the probability that the stress is between 5 and 10? So what are the things that are important in this that we notice in here? Well, that it's an exponential distribution, and that the expected value is 6. So we know that the expected value is 1 over lambda, and that has to equal 6. So I need to have lambda is equal to 1/6. Which is approximately 0.167. So we want the probability that the stress range is at most, which means that it has to be, we're going to say x is we'll say it's exponentially distributed with lambda equals 0.167. So we want it less than 10. Okay, so then what we do is we go back to what our CDF is. Which is, if it's greater than 0, greater than or equal to 0, it should be 1 minus e to the minus lambda x. So let me just try to put as much as I can on the board here. I have 1 minus e to the minus lambda, which is 0.167, and I need 10. So 1 minus the exponential function, oops, I'll show my calculator, minus times 10. So I get 0.8118. Okay. So over here, what I need is 5 is less than x is less than 10. So again, it's the CDF up to 10. Subtract the CDF up to 5. And I've already done that work there, so I don't have to redo it. And over here, it's 1 minus e to the minus 0.167 times 5. And so the answer I get is 0.2457. Okay. So I think in this part right here, I'll call it how the exponential function or the exponential distribution relates to a Poisson process. Now we had covered that in chapter 3. We covered a Poisson process. And remember, the Poisson process was we called it a counting process. It is a counting process. And it counts the number of occurrences of events in a certain amount of time. So for instance, I said I gave you a rate, I told you how much time there was, and from that you could calculate how many instances that would happen in that amount of time. So for instance, if I told you 2 weeks and a rate of accidents on a highway, you could tell me for like 1 week how many accidents we would expect, or the number of accidents and its associated probability. So what the exponential distribution is used for is the distribution of time between occurrences of successive events. So for instance here, how much time between successive occurrences of events. So in this case, we would have events occurring, say at T1, T2, T3, and that interval of time is what we would have a random variable x, and that would be exponentially distributed. And this is what we'll call a Poisson process. So again, a Poisson process is if you give me an amount of time, what's the probability that there is one occurrence, there's 2 occurrences, or 3 occurrences? That's what that Poisson process would give me. It's the probability of the counts. Whereas the exponential distribution tells me how much time it will be in between 2 successive events. Sir, are we always told that it's an exponential distribution, or is there some other way to tell? For us, we'll likely tell you if it's an exponential distribution, and it's quite useful in the sense that it's got certain properties that we use all the time in, say, Poisson processes or Markov distributions. So there's a certain property that we need, and if you need that property, then yes, this is the type of distribution that we'll be using. So to answer your question, probably on the test, we'll tell you which distribution to use. Or we may say this is the distribution we want to use, like an exponential function. Tell us why this is appropriate. Okay, here are some examples for using that exponential distribution. Again, customers arriving at a bank, and I would say time customers so the time between 2 customers arriving at a bank. Phone calls to a college switchboard, again I would say the time between 2 phone calls to a college switchboard. And again, it's related to the Poisson process that we had seen in chapter 3. So here is a very lengthy proposition. We're going to suppose that the number of events occurring in any time interval of some length t has a Poisson distribution with a parameter with an alpha and t. And alpha is the rate of something occurring in one time unit. And that the number of occurrences is non-overlapping intervals are independent of one another. So then the distribution of time between 2 successive events is exponentially distributed with parameter lambda is equal to alpha. So again, you can think of that as a rate. So here is an example that we can use. Calls to a hotline for a laptop help follows a Poisson process with a rate of alpha is equal to 0.5 calls per day. So this means that the number of calls, or the number of days, x, between successive calls has an exponential distribution with lambda is equal to 0.5. The probability that more than 2 days elapse between calls is, so we can write this as the probability of our random variable x so x is the number of days. And how can we do this? Well, we're going to write this as a CDF. So 1 minus x is less than or equal to 2. And we know what the CDF is of that. So it's 1 minus e to the minus, and we have lambda. So in this case, lambda is equal to 0.5. So again, the proposition is saying if it's a Poisson process that we're working with, then lambda is equal to alpha for the time between 2 successive events. So here's our lambda, which is 0.5 times our x, which is 2. So I have 1 minus e to the minus 0.5 times 2, which gives me 0.3679. And that also means that the expected time between successive calls is equal to 1 over lambda, which is 1 over 0.5, or to make this easier for me, it's 1 over a half, which is 2. So this means that the expected time between successive calls is 2 days, which makes sense. Again, you're getting half a call per day. So you'd have a full call every 2 days. Okay. So here's the probability that more than 4 days elapse between calls. And again, similarly, we just using our CDF. So you can see that it's becoming less and less likely that the phone calls, again, this is saying that here's a first phone call. Here's another call. This is 2 days. So we're saying more than 2 days. Over here is 4 days. So you can see that it's gradually decreasing. So again, we would expect a call to show up before then. So for more than 2 days, it's 0.3679. For more than 4 days, it's 0.1353. The number of days increase, the probability decreases. Okay, so is there any questions before we finish today's lecture? Just one last note. So there's some exercises posted. And we have our midterm number 2 in person next Thursday. Okay, thank you everyone for tuning in. If you have any further questions, feel free to send me an email. We also can set up some office hours through Zoom. So, thank you everyone, and enjoy the rest of your morning. Take care.